Okay, so let's get started. My name is Simon. I'm a software engineer from Antwerp, Belgium, and I've been working on Arrow for the last 3 years, mostly on Arrow effects and Arrow optics. And I work at 47 Degrees as a senior engineer. And today I'm here with Raúl Raja.
Hello, my name is Raul, and I am a CTO at 47 Degrees. I've been working in the last couple of years in the Kotlin compiler and meta programming with the Arrow framework and in the Kotlin community. And we're here today to show you a few cool new features from Arrow Meta and the new Arrow FX coroutines library. We cannot hear
Before
you.
we start, we're going to go through the outline of the talk. So today we're going to build a purely functional application, which is built with a new Arrow FX coroutines library that some of you might have seen come up in the Arrow repository yesterday. And we're also going to be using Arrow Meta's type system view in our functional application. But before we actually start, I will take a second to talk about the Kotlin standard library and more specifically about coroutines in a standard library as a base abstraction. So most of you will already be familiar with the constructs or the building blocks that you see here on the animation. And the standard library exposes these building blocks so that people can build powerful coroutines-driven libraries on top of them. One of the most popular or best known implementations is Kotlin coroutines. An important limitation to note here is that there is no notion of cancellation in the standard library. So as I already mentioned, Kotlin coroutines is probably the best known implementation out there today. But today we're announcing Arrow FX coroutines. So let's take a quick look at what both of these are. So Kotlin coroutines exposes a set of constructs for doing structured concurrency with using things like coroutine scope, and it also offers several APIs for doing lightweight features with cancellation support, such as job and deferred, and it also exposes several data types, such as channel and flow. And in the Arrow FX coroutines library, which is also built on top of the Kotlin standard library coroutine system. It has APIs for doing functional effectful programming in Kotlin in an idiomatic suspended style with the same semantics as Arrow's I/O, including cancellation. It also exposes several types such as schedule, circuit breaker, and all your favorite data types that you might be familiar with today from Arrow FX. So what are coroutines and how do they work? So you can see here in the top left, or maybe it's a little bit hard to see, we have a suspend function f that returns a, and the compiler transforms that into a non-suspending function with a single parameter continuation. And that allows the compiler to rewrite your code in a continuation passing style. And here you're seeing it represented as a nested callback style, which you could see as the equivalent of what the compiler generates. But Kotlin allows us, as you can see in the left bottom side, we are allowed to write regular imperative sequential code. What is important to note here is that the coroutines in Kotlin are not limited to concurrency frameworks, and in other languages, it's also known as delimited continuations. And two great examples of non-implementations are the sequence builder from the standard library, or another example could be the Arrow FX DSL for monad comprehensions. So to quickly recap what Arrow FX is and the goals of Arrow FX, it aims to be a battery-included framework to build powerful functional effectful programs in Kotlin in an idiomatic way using suspend with cooperative cancellation, and it eliminates the need for you to wrap your effectful code inside of I/O. And now Raul is going to take us through the app requirements to see what kind of app we're going to be building today.
Thank you, Simon. So essentially, to demonstrate these features, we're going to be building a very simple app whose main requirement is given a list of URLs. We're going to be able to inspect them through a remote service and find structured entities. So structured entities from the unstructured text. So we will see things like maybe mentions to technology or other things in those URLs. And this application is going to be built using the TextRacer API. We have a few requirements around it, we were going to see in a second. And also we're going to be using the, as Simon mentioned, the AeroFX coroutines library, but also some of the new Aero meta type system features such as automatic dependency injection with the Kotlin compiler. So the first requirement that we find is that the TextRacer API requires a key, as many APIs do, and this key must be of a length of 56. And the other requirement is that this key has only alphanumeric characters, so only numbers and letters. And also, of course, if we're going to send a URL, it better be properly formatted in a proper URL, because the TextRacer API library we're using for this implementation is a Java library, and it's going to take a string. So potentially, if you send it a malformed URL, it will just accept it and then fail. So we want to make sure that none of those things happen and everything is constrained. So before we dive into that, the first feature we're going to look at is called type refinements. So think of type refinements as in a type may have multiple values, but you're just interested in those that are constrained by a set of predicates. In this case, we are constraining the type int with the predicate of being bigger or equal to 0 or being even. And as we see, this constraint the range of values that we are attempting to represent for any given use case. Most of the time, people will just use the type int, and then we'll have to write a tremendous amount of tests to make sure that what they're actually modeling is not in the bounds that are incorrect for their model. So why is this a problem today in Kotlin? You could potentially overcome this if we were able to extend types. So this looks like a traditional Kotlin subtype hierarchy. And we can see here a couple of types, positive int and negative int. They both extend int, but this is actually not possible in Kotlin today because int is a platform type, like appearing in the JDK and then further enhanced in the Kotlin language, but you have no way to extend it to give it semantics of being a positive or being negative. So we're going to use composition instead and type refinements to denote these rules. Here's the first example that we see in code. We see the razor key. The razor key, as we mentioned, is a 56 size string. So we can create an inline class that decorates the string. And then this inline class will have a set of predicates, which are the rules that we are determining for the compiler to verify at compile time. We can also see here part of the IDE support in which the type refinement navigates straight to the actual predicate. The next requirement we're going to see is the max number of requests. We noticed that one of the requirements of the API was that we could only do 2 parallel requests. So we want to have a type that also actually enforces that. So we are creating this new type over long, and then we are saying it's range between 1 and 2. So those are the 2 only possible values. And then finally, we have the analysis URL, which we don't want to use Java net URL since it has a side-effecting constructor that throws exceptions. So we can do better in this case. We can just enhance our string to make sure that any string passed on to this constructor, it's actually within the bounds of this really long regular expression, which models what a URL might look like. And then finally, we can see everything in action. We see here that there's no problem here. The type is too long. We can go ahead and fix it. We see the compiler reacting in real time in analysis and then making that as valid now. We see the max request is out of bounds, so we can just fix it and set it to 2. And also we can see that the first analysis URL has a dash, which implies it's not a valid, it's a malformed URL. So we should fix that. And now our domains are properly modeled and ready for the application to receive the proper set of inputs with guarantees at compile time. Now I'm going to hand it back to Simon, where he's going to show us some of these further requirements related to concurrency, parallelism, and what the arrow effects coroutines library can do to help us there.
So now that we have refined our URLs, we are finally able to query text tracer. We have two additional requirements here. One is business requirements, where we don't want to show any exceptions and model our errors in a typed fashion. And we also need to ensure that all the requests that we send to TextTracer happen on an I/O pool, since the Java API from TextTracer is blocking. So we might not know on what coroutine context we currently are when we are calling this function to fetch the results. So this could be any arbitrary coroutine context A. However, we need to run our TextTracer request on a coroutine context B, in this case, the I/O pool. And when that request is finished on that I/O pool, we want that result to be returned to us on the original context, wherever we call this function from. So let's take a look at how we can do this in code. So our first requirement was to represent errors in a typed fashion, and using either is a common pattern for doing so. And here we're using either catch so that we can easily map the error that we receive from TextTracer to the error that we want in our domain. Here you can also see that we are using eval on IO pool to make sure that analyze URL is always called on the IO pool context, since that the Java API from TextTracer is a blocking API. And by doing it in this manner, we can ensure that no matter where you call this function from, that the TextTracer API is guaranteed to be called on the correct IO pool context. Another requirement that came from TextTracer itself is that if you get a result from TextTracer that the analyzed text is not okay, you should not accept this as a faulty response, but they recommend you to retry for up to 3 times. So let's see how we can easily build that use case using schedule. So let's say that we have 2 schedules, a schedule that occur for 3 times and a schedule that run as long as the analyzed text is not okay. We can link the schedules together and we can see here that they are working together. And whenever we have an input that is not okay, you can see that the recurse schedule decrements based on the predicate that was given to the do while schedule. And in case if after 3 times we still didn't get a successful response, the result from the composed schedule will still be a faulty response. So let's see a successful scenario. So here in the first case, we're also going to have an input into our composed schedule. It's going to be a faulty response. So we can again see that the recurring schedule decrements. But in this case, when the do while predicate was matched, so in the case you had a successful response, we will see that the composed schedule finishes with the output, even though our recurrent schedule did not finish yet. So you can see here that the composed schedule takes both schedules into account when running this. So what does that look like in code? Here in code, you can see that we can very easily create a recurring schedule that will recur for n times. And we can also very easily create a schedule that will run while the input is not okay. And we can then easily compose these 2 schedules together using zip. And in this case, we're using zip right, since we are only interested in the output of the do while schedule, and we are ignoring the input from the left side. So in this case, we can use zip right to ignore the output from the left-hand side. So Another of our requirements was to be running things in parallel. So here you can see that we are opening an either block, and an either block allows us to safely extract values from an either using a suspending bind function. And here you can see that we can safely combine other suspending code inside this either block, like a repeat function that uses Raul to repeat analysis URL according to the requirements from TextRaiser. And these either blocks are also available for all your other favorite data types, such as validated lists and many more. And now I'm going to give the word back to Raul, who's going to show us how we can wire all of this together with Arrow Meta.
Thank you, Simon. So basically, as we saw earlier, the subtype system in Kotlin allows us to extend classes and getting hierarchies, and this in a way help us wire our programs. But the limitation is that sometimes we cannot get into these hierarchies. So automatic dependency injection with Meta replaces basically the need for subtyping by function composition. And we're going to take a quick look first at what it looks like. So what do we mean by automatic injection? We mean that the compiler, given a function with a set of arguments, it's going to be able to automatically find one of those arguments or many, whatever you declare. And then instead of having you to provide the argument explicitly when you call it, then the compiler will find the right value for you and inject it in all call sites. This implies that you can create more succinct APIs and DSLs, since you don't have to explicitly provide all arguments, and also your application can be wired at compile time. Besides letting the compiler automatically find those arguments for you, we allow you to explicitly override them yourself. So in any case, at any call site where a given argument might be provided by the compiler, the user always has the opportunity to explicitly pass that argument to the function with whatever value they think it's appropriate of the same type. And then finally, we also have a use case within this type of resolution, which is we allow you for implicit internal overrides. What this means is that if you receive some kind of given behavior from a third-party library that you wish to override, you can also do so locally, flagging it as internal, which comes very handy whenever you want to replace implementations in testing and other different scenarios. So what does it look like this in code? So we said in our application we have a key and a max number of requests. We created a config object for that, and we are annotating that as given. The annotation serves as a provider. And then the functions you see below for key and max parallel requests denote that this entire structure is semi-automatically derived. That is, it also expects that the key is given and the max parallel requests are given to conform the entire object. You see here a fun, but there's many strategies supported. Also, other strategy can be, for example, a class. In this particular case, our class also depends on the Razor config. This is actually the service implementation for the NLP service. It's also given, which means the compiler, whenever someone asks for an NLP service, it will find the Razor one, it will wire it automatically for you and provide you a new instance. So we support function, which will give you pretty much any kind of lifecycle you want. Class, which is a new instance each time. Object, which would be the singleton type. And properties, which depending on how you implement them, they can be singleton or Lrrow type style construction. And now I'll hand it back to Simon, where he's gonna show us some of the requirements in terms of limiting with the actual coroutines FX library the limit of the 2 API concurrent requests that TextRaiser is imposing in our free API.
So in a lot of cases, we want to parallelize our work as much as possible. But in our case here, we need to make sure that we do not exceed the API or the free API limit from TextTracer of 2 concurrent or parallel requests at the same time. So what are some solution arrow effects coroutines that we can use for this? So the first solution that we could use for this is part traverse, and part traverse for a given set of inputs x, y, and z will start running the function f in parallel for all these inputs, and it will then await all the outputs at the end. But this poses a potential problem, since given a large set of inputs, it is also prone, of course, to launch a very large amount of parallel tasks, which could exhaust your system. If you remember from before, our TextTracer API was running on an I/O pool. If we were trying to run 1,000 tasks on our I/O pool, it could be very well that we could go out of memory. However, the problem in our case is that we cannot run more than 2 tasks at the same time, given the limitation of our free API key from TextTracer. So how could we solve this problem? There is a variation on the part traverse N operator that takes a limit to how many tasks it can run in parallel. And here you can see that we specified it to 2. So part traverse had 2 green dots, which it was able to acquire by X and Y. And that allowed inputs X and Y to start running in parallel. And once one of the tasks finishes, it will release its permit. And as you could see here, Y finished first. It released its permit to Z, and that allowed Z to start running. So let's take a quick look at this animation again. Here you can start it with 2 permits. One was handed out to X, one was handed out to Y. They both start running in parallel. And when Y finished it, it released permit. Then Z, which was waiting, acquired the permit. It can also start running. And once it finishes, it also releases the permit. So when all tasks have finished running, we again have 2 permits available. And by this, we can guarantee that no more than 2 tasks are ever running in parallel at the same time. So in code, that can look like this. So again, we are opening an either block, which allows us to safely unpack or extract the values from an either, which in this here we're doing inside part traverse N. And we are using traverse N to parallelize the request to TextTracer. But if you notice here, we are also limiting the maximum amount of requests that was provided by the given Razor configuration that Raul showed us before. So here we can actually write our code in such a way that if we would pay for the license later, we can increase the amount of parallel requests that are going to run without having to change any of this code. We only have to change the configuration. So finally, Raul is now going to show us how we can fulfill the last requirements of our application.
Thank you, Simon. So the last requirement of our application was to actually be able to hide the complexity of this implementation behind a very simple API. And for that, we're going to use a type system feature called coercion proofs. And what we're going to try to do is project our entire program and hide it inside the list of URLs and provide that as an API to obtain structured entities. So what does it look like? It's as simple as this function. This is a coercion suspend function that is projected over the type list analysis URLs. And then it returns either an NLP remote error or a set of entities. And here we can see our entire program running hidden, which is given implicit or a provided compiler NLP service from our dependency injection. And notice here we are not using constructor-based or method-based or anything in particular, because dependency injection in Arrow Meta works in all expression positions, not just constructors. So here we can just demand the NLP service called fetch common entities, and then finally see what this will look like from the point of view of the user consumer API. Someone will provide a key. The key gives proof they can access the Razor API. the number of requests they are bound or constrained by, and then a final program that takes you from a list of entities to an NLP remote error or a set of entity. And you can see here that there is a warning. We can make this coercion implicit, disappears. We see on the left-hand side, the entire program is now hidden. Now we can make it back explicit if we want it. But coercion proofs essentially allow you to bridge the gap between two types that are not subtype of each other's, but you can establish such relationship, then resolve it with a function, which is what we are doing here with the final coercion function proof. So as a conclusion, we had a set of requirements for this application, and we try applying precise domain modeling with type refinements. We guarantee the compiler can inject our entire dependency graph with given. We've also used APIs that were limiting, and then we're imposing real use case scenarios that you might find in the real world, like limitations, and you have to work around them, like the text tracer API. And finally, we were able to see other proofs, like the coercions, which allows you to express subtyping as functions in a way. And that's pretty much all we have. We hope you enjoyed it. We'll be happy to answer any questions. And before we go, I would like to thank you, the organization, for inviting us to this talk. I would like to thank the Kotlin community and the Lrrow community for participating and making everything you saw today possible. And I would like to make a special announcement that if you're interested in this type of content, you can come and contribute. If you want, we offer one-on-one mentorship. And we also are about to launch from 47 Degrees an academy initiative that is coming up pretty soon, so stay tuned, where you will be able to enjoy more of these style of animations and content regarding to Kotlin, Scala, Haskell, Swift, and many other topics. Thank you so much for your time, and if you have any questions, I'll look forward to answer. And thank you, Simon, for sharing this opportunity with me.
Yep. Thank you, everyone, and thank you, Raul. One thing that I quickly wanted to add is if there's any questions, we will also be hanging out in the Kotlin Slack channel later if anyone has any more elaborate questions that we cannot fit in here right now.